Okay, so hey guys, I'm Rick, and today I'll be discussing, as mentioned earlier, semi-simple algebras, and given some time, maybe representations of SLN. And generally we're super interested in these structures because Lie algebras appear a lot in math and physics, infinitesimal changes, continuous symmetries. So yeah, let's get to it. So first, let's look at the definition of what a Lie algebra is in the first place. So a Lie algebra is, so I'm going to use frac G for this. So let G be a vector space over the field complex numbers with a binary operation that looks like this, and we use like a bracket. Map here in a sense two elements of the vector space, and it sends it to the third element such that it follows the three following. First is that it is a bilinear map, so it's bilinear. Second, it's alternating or antisymmetric, so that means that the Lie bracket of x and y is equal to minus yx. And third, it follows this property called Jacobi's identity, which I'm not going to write out fully for the sake of time. But essentially, you have two more terms that look like this, but you're just cyclic in removing these. And you can think of this bracket, a very common binary operator. It's just the commutator. So AB minus B. So this is the one that we'll sort of think about and focus for the rest of the stuff. And so I'm interested in semi-simple, which essentially means that it can be decomposed into its more basic constituents, like this. So this is semi-simple if it can be written as a direct sum of a bunch of simple Lie algebras. And what's important is that these are sort of the building blocks of the more complex Lie algebras, and there's a whole classification developed for simple Lie algebras, but this is just something to point out. And so some examples Lie algebras include, perhaps it's like one that everyone has seen before. It's just the space that we all live in and love. It's R3, equipped with the cross product. So that's one. And another one is SLN, which is the one that we'll be focusing on. And this is just a set of all n by n traceless matrices. And by traceless, I mean the sum of the diagonal entries sum to sum. And specifically, there's a very well-known example, SL2. And SL2 specifically has a very nice set of generators, which are labeled by H, E, and F. And these are just 2 by 2 matrices that look like this. And if some of you guys have taken quantum and flow theory before, then you'll recognize that this is the Paley just for fun, but it's not what it is. But the most important part about these Lie algebras is that most of the important information is encoded within the Lie brackets and the relations regarding the Lie bracket. So here specifically, I'll write out that, and also the Lie bracket for SLN is just a commutator like we have it. So HE is equal to 2E, HF is equal to 2F, and EF is equal to H. So here. Ultimately, the Lie algebra that I'm interested for this talk is SLN. And let's take a very interesting look at a very interesting decomposition of SLN, which is the following. So we can write this as a direct sum of these spaces, and I'll explain in a moment what these are. So these are just a set of all n by n traceless matrices, but then somehow we can decompose it like this. So frac H here is just a set of diagonal traceless matrices. And these are a subset of SLN, so these form a subset. And then EIJ on here is just n by n matrix where IJ, the entry on IJ is 1 and everything else is 0. So how can this even be? Well, I think the first step that we should do is just investigate how elements of this guy acts on EIJ. So if we take some element H, so it's diagonal, so it's sort of label it with like D1 through Dn, and we see how does it act on Eij. And the way elements of this act on Eij is via that commutator, the lead bracket. So we can do Eij, and it turns out that you get an eigenvalue equation. It turns out that this is equal to Ei minus Tj on Eij. So you have this like nice eigenvalue equation, and then you might be wondering like, how is this part related to H? Well, it turns out that this is the same thing as taking the differences of these two maps, which are linear functionals that project onto the ith and jth coordinate respectively. So if you take like Ei and you take d1 all the way to dn, then you just get out Ei, and then you just apply this on H. And so you now have this like sort of interesting eigenvalue equation with respect to this action of H on Eij with this, and so you can create sort of eigenspaces, and you're using eigenspaces to decompose this vector space. And so ultimately these are called, so Eij are the roots, these are the so-called roots of SLN, and we can label these by like alpha Ij, and we can write then the eigenspace as this. G alpha Ij is the set of all x's, and G such that when you act H on x using the Lie bracket, then you get like alpha Ij of H for all H. So now let's consider a representation. So let V be some finite-dimensional representation of the Lie algebra SLN. And just to clarify again, representation essentially you're just defining an action of the Lie algebra onto the vector space. So like you can sort of define different ways to transform the vector space via this Lie algebra. And you may be more familiar with like group representations, which are the same idea. So if we let V be a finite dimensional representation, then we can sort of similarly like that, we can decompose it into eigenspaces, lambda, where the lambda is the set of all small v in this representation, big V, such that when you have H acting on V, then it just acts by lambda. Like this. And okay. So here we have roots, and I want to mention that here we have weights. And both of these are linear functionals in the sense that they take in a vector and they output like a scalar. And so, I'm just move to this board here. The neat little fact is that these roots and weights can interact with each other. And specifically, if you take an element of this root space and you act it on an element of like V lambda, then it acts as sort of like lowering and raising operators that you may see in like other fields or like even like quantum mechanics, for instance. And so, how does this relate to like representations? It turns out that just showing this here real quick. Yes. So we can now then define. So you have like roots and weights, and you can define what's called a weight lattice. And so a weight lattice is essentially the set of all weights that can correspond to like some representation of SLN. But it's written as P is equal to, for SLN specifically, it's equal to the span of all these like linear functionals that are projections, and you mod out by this ideal epsilon 1 plus epsilon n, and this just comes from the fact that the diagonal has to sum to 0. Then you're spanning this over C, I should say. So you have this, and finally you can actually take a subset of this, which are called sort of dominated or dominating integral weights. And so the main sort of theorem is that there is a nice correspondence between the dominating integral weights.
You look 37.
Okay. With the building blocks of the representations of SLN, which are called irreducible representations. And, this is locally known as sort of highest weight theory. But yeah, thank you.
Are
questions for our speakers?
I have a question. So you wrote down this Lie algebra with lowercase curly s, lowercase curly l, sub n. Does it have any relation to the matrix group SLN?
Yes, it does. It has a very significant relationship. In fact, it's related to SLN, set of n by n matrices with determinant 1. And roughly speaking, we can view this group also as a manifold. And if we take the identity and we look at the tangent plane at the identity of the manifold, then that forms a vector space, which turns out to be the Lie algebra. So the corresponding Lie group for the Lie algebra SLN is indeed the special Lie group. And there's an exponential that I can institute. Yeah. What's your question?